High sensitivity, on the other hand, usually it's a very wide opening and a very short septa. So let's say that we go to a 4 millimeter opening and we make this 2 millimeters. Okay, so this is going to let in more photons, but it's going, this will give you a lot of counts, but it's not going to give you a very detailed picture. Remember, we said the trade-off between these two. The higher the resolution, the longer it's going to take to get counts. Okay? Does that make sense? Now, the all-purpose is kind of a hybrid of these two. So basically, if I make this thing 4 millimeters long, and let's say that we make it 2.5 millimeters in diameter, okay, it's kind of a cross between these two, so it allows me to get, I'm sacrificing a little bit of sensitivity, I'm sacrificing a little bit of resolution, but like I said, it's an all-purpose. I can use it, for a flow study or a high-resolution image. Okay, now back in my day, like I said, when we did a flow study, let's say I'm doing a renal study, okay, I had to put on the high-sensitivity collimator because I'm taking one picture every 2 seconds if I was doing a brain scan. Okay, inject the patient, do the flow study with the high-resolution or the high-sensitivity collimator, and then I take the patient out, put on the high-resolution, and we take the detailed pictures. Okay, make sense? With an all-purpose, all I have now is 1 collimator instead of 3. Okay, so that way I can do my flow study, and I can do my delayed images. I don't have to change the collimator anymore. Okay. Then the next thing that I want to talk about is the crystal. Typically on your board exams, they're going to ask you what each component does. Okay, so the collimator only allows photons traveling in a certain direction to reach the crystal. Okay, and then as you've learned about the crystal, we know that it's surrounded by aluminum because that is not a very high atomic number. We don't want the photons being absorbed. Yeah, Monica.
Before you go on to the crystal, can you just talk really quick about the pinhole collimator?
Oh, okay. Pinhole collimator. If you've ever had a pinhole camera before, probably not, but if you ever take a photography course, basically the pinhole collimator gives you very good resolution, and normally they'll have, like, you can change the aperture here. You can unscrew this, and you can either put like a really tiny hole, medium hole, or a really large hole. At least mine does. I don't know if your guys' do. Some of them are fixed. Okay, now the thing about pinhole collimators is that the images are reversed. So you have to be very careful when you use pinhole collimators to make sure you check your right and left and everything. Okay? But what happens is this, okay, there's a focal point somewhere here. There's a focal point here. By changing these openings, it changes that. Obviously, if you bring the pinhole collimator closer to the patient, it makes the object larger. If you move it further away, it makes it smaller, so you can minify and magnify an image. There was one hospital that was actually putting a pad on the floor and doing their bone scans with the patients lying on the pad. They're doing a whole body pinhole bone scan.
Pinhole?
Yeah, pinhole. Nice pictures.
Yeah.
But the thing is, it's not very practical. Okay. you know, most of your patients that aren't feeling very well and having them lie on the floor and, you know, blah, 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 it just didn't work out too well, so. But anyway, so this is a pinhole. These are the apertures that they use for them, or you may have available. You know, as I said, what they've done is they have started limiting the number of choices we have. Pretty much now you just have a low energy parallel hole, medium energy parallel hole, and a pinhole. They may call it medium energy high energy, but it's not. There's not enough lead in it to be that. You've seen that when you do a whole body scan with I-131 and you see those little, you know, star-shaped artifacts. Okay. So, the first thing that we need to understand, what does the crystal do? And this kind of goes back to what all crystals in general do. Does anyone remember the layers of a crystal? I mean, as far as like the bands or the energy bands? Remember, we have a valence band down here. What's the next one? What's the one in the middle? This is an X-ray question, X-ray people. Okay, basically crystals are constructed, this is where all your electrons or free electrons are. And then you have what they call a forbidden zone, where depending upon whether this is a insulator, semiconductor, or a conductor, that determines how wide this forbidden zone is. And then you have a conduction band where electrons are carried off. Okay? So, what we did, if we think this as a sodium iodide crystal, what we do is we put in an activator. Normally it's these two little dots and we'll say thallium. Okay, basically thallium takes up residency in the forbidden zone, and when the radiation comes in, the electrons are knocked off. They're temporarily held by these little electron traps in the thallium. So they're held there, and then they're allowed to return, and when they do, they give off light. Okay? They scintillate. Okay? Now, what's important about that is how much time it takes. You know, once the electron has been removed, how long does it take to go back? How long does it take for the atom to get itself back in shape? You know, it's like if you guys drink a cup of coffee, you might be wired and hyper for a while. How long does it take you to get back to normal? Assuming that's what you would like to be, right? Trying to stay awake in the hospital and drinking coffee, that's something thing. Okay, so the first term you need to learn about the crystal is this, okay? The luminescence, converting invisible photons into visible light. Okay, that's luminescence, that's the process. And that's what we're doing, is we're causing the photon to be absorbed by the crystal.
What did you say again? Luminescence was invisible photons?
Yeah, well, luminescence, okay, basically you have a very high energy. This is 140 keV. Well, let's make it 1 keV. Let's just make it 1 keV because that's easier to understand. Okay, that's an invisible beam of light. You know, the visible light spectrum is about usually 1 to maybe about 4 electron volts. So what you're seeing right now is very, very low energy. So this energy here, you wouldn't be able to see it. But when I have it interact with my crystal, it's going to ionize and excite this crystal. Basically, it produces about 29 Compton, and then it's finally slowed down. Remember, every time there's a Compton interaction, it loses some energy. So on interaction number 30, it's photoelectrically absorbed. But what's happened, though, is this crystal has been ionized 20 or 30 times altogether. Okay. Now these are, of course, these are outer orbital electrons. This is an inner orbital electron. But in any case, when those vacancies are filled, they're all going to give off light. So we're going to get 30 light flashes from that. Sometimes I call that conversion efficiency. Basically, it's the amount of light produced per photon. But, so does that make sense so far? Okay. Now, once the light has been emitted, okay, if it takes a long time for those 30 light flashes to be given off, then we say the material is phosphorescent. It continues to glow. If the electrons are able to get back very quickly, then we say that the material is fluorescent. Okay? So basically that's the only difference between fluorescence and phosphorescence is how long is it going to take for these atoms to pick up an electron and get back into their original electronic state and give off this light.
Would that be the dead time?
Huh?
Is that the dead time?
Yeah, basically. But it's not really considered dead time like we talk about with a Geiger counter, for example. But yeah, anytime we actually have a term for this. It's called temporal resolution. Okay. In other words, if you have a high quantity of radioactivity and you want to take a picture of it, what's going to happen is you are going to lose information. I'm going to bring my maybe I might be able to show it later. In the Christian book, Nuclear Medicine and PET-CT Imaging Principles and something or other, there's a good picture of what happens when you have too many counts. You actually lose resolution. The pulses pile up, the gamma camera can't process them as efficiently, they lose information. Okay? If two photons hit at the same time, it doesn't know whether that was a 280 keV photon or was it a 100 or 140 keV photons. So we call that temporal resolution. Okay. That's why we tell you guys when you make up a flood to do your quality control, don't put more than about 30,000 counts per second, because most gamma cameras can't handle more than that. Okay. But so going back to our story over here, okay, what we're actually looking at is this term called the decay time. So after those 29 or 30 interactions have occurred, how long it takes for 67% of them to get back is how we calculate the decay time. If it's less than 10 to the minus 8 seconds, then it's fluorescent. If it's longer, then it's phosphorescent. Okay. There's some crystals that we want that property of them. You know, for example, if you have a watch that glows at night after it's been exposed to light, you want it to be phosphorescent. But for a gamma camera, we don't want it. We want it to be very fast so that we don't degrade the quality of our image. So that's what we're looking at with this decay time. And then, like I said, the sodium iodide crystal, we like that because it has relatively high density and atomic number. We said the thallium is in there, so it helps trap the electrons so that they can be released a little bit more uniformly at room temperature. You know, some crystals have to be heated, some have to be frozen. Can anyone think of a crystal that we use that has to be heated? The one that you wear on your finger? You guys have finger rings?
Of course.
Okay, do you guys know what's in them? No. How do you know there's anything in there?
You can hear it.
Okay.
It rattles.
If you were to take that little piece of paper that has your name off, you're going to see there's a little square chip in there. Okay? Does anyone know what that little chip is made out of?
Crystals?
Crystals. You're scaring me, man. Yeah, you're really scaring me.
Sodium iodide crystal?
No, not sodium iodide. Okay, it's made out of lithium fluoride. Okay? Lithium fluoride is what they use for your finger ring. Aluminum oxide is what they use for your Luxel badge. Okay?
So should we not use our ring or leave our ring badges in the car then?
It's not going to affect them. The same thing with, back in the old days when we had film, actual film, it was a problem. If you washed it or exposed it to heat or had it out in the sunlight, it would give you a false reading. The Luxel badges, they're not sensitive to that. They're very, not delicate. The lithium fluoride, same thing. Very environmentally friendly, so to speak. But the thing is, in order to read the lithium fluoride, it has to be heated to 500 degrees. They put it in like a kiln, like they bake ceramic pots and stuff in. When it gets up to 500 degrees, the electrons are allowed to go back to their original position, and they give off light in proportion to the amount of radiation they're exposed to. Okay? And then they have this device here measure the light. Okay, this is a PM2. If you look on the inside of it, okay, it's basically cesium iodide. It's a cesium iodide. It's a cesium antimony material down there in those wires. Okay, when light hits it, it knocks electrons off of that. And then over here, see this thing that looks like a ladder? There's like 10 little ladders here. Okay, each one of these is charged with 100 positive volts. So when an electron is knocked off here in the photocathode, it's accelerated with 100 volts of kinetic energy, and it hits this copper. These are called diodes, by the way. So when it hits that diode, it's like playing pool. You have all the cue ball, or you have the cue ball, and then you have all the other balls. When the cue ball hits the other balls, it kind of knocks them all in different directions. So when that one electron hits the electrons in the copper, it knocks some of them off. Then those are accelerated to the next diode, and they knock more off. Yeah, Monica.
So when they heat our badges and stuff to read them, the electrons go from the conduction zone back to the valence zone?
Well, they go from the forbidden zone back to the valence bands. And when they do, they give off light.
So do they ever go to the conduction zone?
No, not usually. Only if we have it set up as some type of like a semiconductor. So in other words, if I want to create a circuit with it, if I move the conduction zone or the conduction area closer to the valence zone, then I create a conductor. If you guys were to look at copper, for example, because this is what we have here, copper. Materials that are used as conductors, basically you have overlap between the conduction and the valence zones. Okay. A semiconductor okay, here's your conduction. Here's the forbidden. And here's the conduction here. You have there's some, should we say, barrier to keep the electrons from jumping into the conduction zone. But then, this is a semiconductor. We use semiconductor detectors too. I don't know if you're aware of that. So if I have a really wide forbidden zone here, then I have an insulator. Okay. But the thing is, like with this one here, as I said before, the process that we're actually discussing is the light comes in. Well, let's just sort of draw a picture of it here. Here's a crystal, okay? Here's the collimator. Here's the PM tube. So if the photon comes in, it's absorbed in the crystal, and light is giving out in 360 degrees. Remember, I think I showed you some pictures of uniformity floods, and you can see this dark area on the outside edge of the crystal. Okay, that's what they call edge packing. Okay, the edge packing is because the light that's traveling horizontally, when it hits the edges, it's reflected back up. And because there's more of it than there is stuff that's sitting in the center, that's why you get that ring on the outside edge. Okay, that's called edge packing.
Because it's more dense.
No, what's happening is you just have a lot of light that's traveling horizontally. Okay, what you want is the light to travel vertically towards the PM tube, but see, some of it travels sideways. I mean, it goes 360 degrees. That's why we put reflecting powder down here, so that any light that would be reflected down this way, instead of being lost, we try to reflect it back up into the PM tube. Okay, all of this light that's produced in here helps the gamma camera determine what energy of radiation it's trying to detect, because the amount of light is proportional. So I told you that if I have 1 keV here, it's going to produce 30 photons. If this was 2 keV, it would produce 60 photons, so it would be twice as bright. It would produce twice as many electrons. So that's how the gamma camera is able to tell us what energy we're looking at. Okay. So what happens then is, okay, so the photon comes in, it's converted to light in the crystal. The light then interacts with this thing called the photocathode. And photo means light, cathode means source of electrons. Okay. The number of electrons that are knocked off is proportional to the brightness of the light. On average, it takes about 5 to 7 electrons to knock off 1 electron. So if I have 30 photons here, and it takes 5 light photons to knock off 1 electron, that means I'm going to get 6 produced here. If I had 2 keV come in, I would have twice as many electrons knocked off. Okay?
Knocked off the PM tube?
No, knocked off of the photocathode. Okay, what we're looking at, okay, down in here is the photocathode, and it's made out of cesium and antimony. Antimony is a material that when it's exposed to light, it becomes ionized. Oops. Now the photomultiplier tube, okay, so the number of electrons that are knocked off are directly proportional to the energy of the photon that was absorbed by the crystal. Okay. What you have to understand is that this proportionality is maintained all through your gamma camera. This is why when you go from a, say, technetium to indium, basically what you're doing is you're telling it to look at 280 keV photons, which produce twice as much light. But what's going to happen then is those electrons that are knocked off are going to now be attracted to these dynodes. And so the dynode has 100 positive volts on it. When these electrons hit, they knock off about between 5 and 7 electrons per electron here. So I started with 6. Each one of these is going to knock off 5 electrons, so now I've got 30. And if I have another dynode over here, these 30 electrons are going to be accelerated to that one with 100 volts of positive energy. They're going to knock off 5, so now I've got 150 electrons. Yeah, you multiply that times 10 dynodes. By the time this one electron gets up to the 10th one, it's been amplified by a factor of 1,000,000 times. Okay? So you have, like, let's say, a millivolt. Okay? But that's another consideration there, is that, we'll talk about the PM2 here in just a second, but why did we select thallium? And why did we select sodium iodide? Because in radiology we use cesium iodide. Well, some of the things that we looked at, okay, first of all, the high density. Okay, you want to stop the radiation and detect it. So low density materials are not good. So here we have 3.67 grams per cubic centimeter. That's fairly dense for a crystal. The other thing is you want to make sure that it's the right wavelength that's compatible with your PM2. 4100 angstroms is kind of like in the ultraviolet blue range, and PM2s love that. So it's a blue light. If it was a red light, wouldn't be as good. Okay? The brightness, okay, notice 210 versus 55 for cesium iodide. So it's basically 4 times brighter. And this is a much better pulse. The decay time, in other words, if we were working with high counts, you inject 25 millicuries, this would give you a better picture because it's 4 times faster. Decay time is 0.25 microseconds versus 1.1 microseconds. The crystal size I put down here, this number has changed. They're square. I don't know what they are anymore, but each manufacturer is making them pretty good. And the other thing is the thickness. And again, here we have a trade-off. If I want really good resolution, then I use a thinner crystal. If you guys go to a restaurant and you order wine, you normally serve wine in very thin glasses. You can see right through it as if it wasn't there. If you get a glass of water, they normally have it in a thicker glass. It's more difficult to see through it. It's the same thing with your crystals. So the thicker ones, they're better at stopping the radiation, but you lose resolution. And there's all sorts of things that they do to try to trade off better resolution. For example, we put a uniformity computer in with the thin crystals. So you guys may have a uniformity computer that you have to take a picture with it on and then with it off. If you have a thick crystal, then they put what they call light guides or light pipes, so that the light isn't as spread out when it reaches the PM2. There's just all sorts of weird things that they do. Okay? But just basically keep in mind that the thicker is better stopping power, thinner is better resolution. We already talked about why the crystal is encased in aluminum. And then I've listed here all of the different types of reflecting powder that they use. Titanium dioxide is the most expensive because titanium is an expensive metal. But just make sure that the light that's reflected away from the crystal is going back towards the PM2. The total light absorbed in the gamma camera, there's 3 pieces of information that we need to get in order to get a picture. We need to know the X and Y coordinates, so where did the radiation strike, and then if we add all of the light energy together, we get the Z-pulse. So when you guys are looking at the energy spectrum, or when you're telling the machine to count after, to stop after 500,000 counts, what you're counting is the Z-pulse. The Z-pulse is the X plus the Y added together. That equals Z, for the Z-pulse. That's your energy pulse. Okay? So that's what the computer looks at to tell you whether we need to reject it or accept it. Okay, the light pipes, like I said, you may or may not have these on your gamma camera. Usually if you have a thick crystal, to improve resolution, they have light pipes. These things look like test tubes. Okay, that's exactly what they look like. They're like glass test tubes. And the light pipes can be thick or thin. So if you have thick light pipes, then you have a more uniform looking image. If you have thin ones, then you get better resolution. So that's you know, not all of them have it, but you would know if they did. Okay. So they also put down that they're also called light guides. Okay, then the PM tube, we'll talk about that since it's 12 o'clock. I'll let you guys get some lunch. Alrighty.
So light pipes really help with better resolution, and what helps to get better sensitivity? The flood, what's it called? The flood.
Oh, you have a uniformity computer to get better, fill in the areas that they have problems.
We're going to lunch now?
Huh?
We're going to lunch now?
Yeah, well, the date's till 3.